course, what we've been discussing today is mainly this, image representations. So what is image representation? Well, using a little bit of natural language, an image is just some data x, and you get an encoded function phi, which is your representation function, and out to get a vector, all right? A high-dimensional vector, which presumably is useful to do something. For example, labeling the image content. But this could also work if X wasn't an image, it was a piece of text or some audio. You could use also representation to try to solve some data understanding task. And of course, the way we do image representation these days is by using deep convolutional neural networks. You already seen this slide before. This is half, or maybe 3/4 of AlexNet. This is the way it was presented in a Krzyzewski paper, probably because these models are so big that you need to compress them somehow, for example, by cutting them. Now, these models are great because, of course, what you care about is performance. And these representations are what give you the best performance in terms of, for example, classification accuracy in an image labeling task. But not only that, I don't know whether it was discussed a lot today or not, but one very good thing about these models is that they learn a sequence of representations, so you can cut them everywhere here along the depth, and how to get a vector, which is a representation of the image, that in its own right can be useful for some other task. For example, you can train this network on AlexNet and then use it on some other data set. For example, live feed, and it will still work. I was going to see in a minute. Now, what's the bad news here? Well, the bad news is that it's a black box, so we don't really understand what it does. So you have learning millions of parameters, and if you're a computer vision scientist, you might wonder what are these parameters for, what is happening inside this network. So the meaning of these operations is not really clear. Now, going back to the point of how complex these models are, so this is AlexNet in 2012. This is a schematic, and I think each yellow box here is a layer. And this network had about 500 convolutional layers and 3 fully connected layers, which, by the way, do not exist. They're just convolutional layers, which get a different name for reasons about geometry, but it doesn't really matter. In essence, this is 8 layers, all right? Then, this is what happened in 2013. We got VGGM, which was a bit better than AlexNet, just more filters, and then, of course, VGG very deep, which was a very deep network because, hey, it had 16 layers, or maybe 19 layers. So what happened next? Well, in fact, at the same year, there was another network which was in fact somewhat deeper than VGG very deep, which was BMVA. And these two models worked about the same on our main benchmark, which is ImageNet. And if we go on with this, you know where I'm going. So the next step was ResNet. ResNet is what is popular this year, and next year is going to be something else, I'm sure. The smaller in the ResNet has maybe 30 or 50 layers, so it's this. And you can see the comparisons compared to Inception. And the one which works the best, the one the challenge I believe this year, has 152 layers, so it's this guy here. All right, so it's pretty big. So that is important. I would not say that this is necessarily more complex than VGG very deep, because if you look at the number of parameters, they're actually very comparable, surprisingly. It just means that in ResNet, all these parameters are spread along many more layers. All right? But nevertheless, these are very, very big models, and we don't really know what they do. So what I want to talk to you today is some of the research we're doing, not just about creating better models, but about trying to understand them. And we're going to dive into two things. One is visualizing deep networks, and the other one is to try to probe some of the properties that these deep networks actually learn automatically from data. But before I do that, I would like maybe to just to give a sense of what this network can actually do by showing a little demo. And I think there is nothing better than a live demo, actually. So if I can restart MATLAB. Once again, you should never change screen with MATLAB open. That's the first thing you need to learn. All right, here we go. And let me just mirror my screen, because otherwise I won't be able to see anything here. All right. Okay, let's see. So, this is, I believe, the Inception, actually. It's not even VGG very deep. So here you see this network working in real time on my laptop. It's not using an NVIDIA GPU, although I have one on my laptop. This laptop sucks. It's 3 years old, so Kingsbury doesn't, I mean, Inception doesn't actually fit in there. But you can show it things. Let's see. There you go. So CAP works very well. You can show it iPod. Well, it's an iPhone really, but you get my meaning. And of course, this has been trained on ImageNet, so I don't really have ImageNet images with me, but I can show it some pictures on my iPad. You see the amount of reflection that there is. Nevertheless, and this is the sort of speed you can this network actually works at just on a CPU on this laptop. All right. So if you were to show me this, like maybe before 2012, I would say this was fake. This time was completely fake. But this was completely impossible in vision before deep learning. But deep learning, of course, is not just for image classification. You can do many other things. For example, here I have a fairly new demo of, this is the first time I'm showing public actually, of a network that does key point estimation. So I need to get a little bit away from my laptop. And this is a bit slower because it takes about 2 seconds to process an image on my CPU. But it works fairly well. So each color block there is a different marker, essentially, which network is estimating roughly in real time by running a network which is a derivate. So if you can strike a pose, I guess, and it should still work. So this is also a way of embarrassing yourself. But as you can see, it's very, very robust. All right. And I think if you turn around, you might be able to pick up that the two-side switch actually. Yeah, I guess. Let's see. Turn around more, I guess. I guess. So you can see that from the colors of the blocks, all right? So you can distinguish back the count. All right, so this is sort of things you can do with deep learning. And this was running in MATLAB using our toolbox, which is MatCombNet, if you're interested. I mean, not everyone uses Torch and Lua or Python, fortunately for us. But now let's dive into the technical topic. Fun is over, so I'm going to start by describing visualizer representations. All right, so first of all, a little bit of theory, if I want to call it that. So what are we trying to achieve here? So we have seen before using networks for creating images for the purpose of, well, getting out essentially pretty pictures. And what we're going to do here is to get also some pretty pictures, but for the purpose of understanding what the network is doing. So the main goal here is not to get something nice, but is to get something useful, all right? So this is the situation. So we have an image space where our image lives, and for now is empty. And then I have a point here, which is a representation of the image, right? So that means the output of a deep network, which is a high-dimensional vector. And here I'm plotting a representation of that. This was, in fact, not the output of a deep network, but the output of hog features. This doesn't really matter. It doesn't matter which nature representation you use. It works for any, even classical representation in computer vision. But there you go. So at the end of the day, what you get is a vector into some abstract vectorial space. And what you can do is play this game. So you can try to invert this back onto an image. All right. So you can give this amount of information here. You ask yourself, all right, which is the image that is produced by this presentation, and you do that by computing essentially the inverse. All right. Can I always do that? Well, not exactly. And the reason is that the inverse would be an image here that maps to my representation, give me this vector. But in general, you see that there are multiple images in this image space that give me exactly the same vector as output. All right? So that means that the representation in general is not a one-to-one map. All right. Why is this important? Well, because the whole point of representation is to abstract away from the details contained in the image down to a synthetic and accurate representation of the content. For instance, these two images are both images of dogs, although they look very different because the color has been lost. I would expect that at some point in my representation, these two images will be collapsed onto the same vector, right? So now what I can do is to try to invert this guy, acknowledge that in general, I'm going to get more than one inverse, and by looking at the sort of inverses I get here, I can get a sense of the information that the representation is throwing away. So in this way, I can learn about the invariances that the representation has learned. All right? That's the key idea. So how can I do that in practice? Well, it's actually computation is very simple. All I do is I set this as an optimization problem. So I start with an image, that's my reference, and a computer representation, say some intermediate layers in AlexNet. And then what I want is to find a second image X such that the representation of x is very close to the representation phi naught, which is what I got from the reference image. So what does it mean is that I'm going to have a second image x here that I find through an optimization problem starting from noise, such that the representation of this guy is the same as the representation of the reference image. All right? And so at this point I have two images, the original one and a new one that I found by optimization, that happen to have the same representation. So these are both inverses of the same vector, okay, through the representation function. And importantly, what I'm going to do here is to start to generate, I will generate these images starting from white noise, all right? So the only information that the process has about the original image here is this vector there, all right? So just from this, I want to be able to reconstruct something out and see essentially in this way which information is preserved in that vector. Now, I'm going to do only one more thing, and that is to add some regularization into this process. Why I do that? Well, first of all, because if you try this directly, it doesn't work very well. But if you add here some simple regularization which require the solution to be relatively smooth, for example, apply on TV normal the image, which penalizes diffuse gradients essentially, or perhaps change exponents so you get a sort of Gaussian smoothness prior, what you get is an image out which is much more intelligible. All right? Now the point here is that whereas this is adding information to the process of inversion because it's requiring your solution to be smooth, this is very generic information. All right? So this is not about a dog, it's about the reconstruction being a little smoother. So it's a very, very tiny amount of information that you add. All right? There are many visualizations which are related to this one, including decomponents that we have seen before. And by the way, we have a new paper on decomponents, hopefully coming out in ECCV this year. We'll see two next week, I guess. But what I want to tell you about specifically inversion. So here's a schematic representation of AlexNet, even more schematic than the one we have seen before. So these are different layers in architecture, and I guess the green ones here, or the orange ones here, are the convolutional layers, and the rest are the nonlinearities, max pooling, and etc. So what I'm going to do is to show you reconstructions from these different layers. All right. So here's what happens if I take my input image, feed it through the first layer of AlexNet, and then running the inversion process. As you can see, I reconstruct an image which is essentially identical to the original one. Right? That means that the first level of filters, they do not throw away essentially any information, which you might expect. Okay? But as you go deeper, you'll see that your reconstructions start to become fuzzier and fuzzier. And the thing to notice here is that the exact location of some of the details in the image, they start to shift around. So this is you can expect, because you know that these little shifts of bits of the image are not so important for recognizing the object. In fact, you need to be invited to those because this sort of deformation is what you might expect to affect the image in practice when the monkey moves around a little bit. Now, this is not replicating a natural motion of the monkey, because it cannot, but it's trying to compensate locally for this kind of little deformations that you might expect a monkey image to have in practice. As you go deeper down, very interesting things that start to happen. So here, now we've got the monkeys with 3 eyes, all right? Now, it is important to understand that from the viewpoint of the network, of the model, if you cut your network at this level of depth, then this guy and that guy are completely equivalent up to some epsilon network reconstruction, which is generally very, very small. So for the network, this is a monkey which is just as good as that one, all right? So this also shows that while these networks are really good, at the same time, they do not have a perfect understanding of what an image actually is. Which is obvious, in a way, because they are trained discriminatively. So there is no reason why they should be able to reconstruct perfectly a monkey unless you train something like GAN, which is designed instead to give you a nice image back. But this is, again, meant to show you which information is being thrown away by a network that does classification instead. All right, so you get deeper. And then, finally, as you switch from this convolutional layer to these fully connected layers, I said that they are the same, and this is true mathematically because they're just, linear operators. But fully connected layers happen to have filters which are as large as the input tensor. That means that a filter in a fully connected layer sees information from the whole image. It's not local and transition invariant anymore because, well, it would be, but it's applied to the whole of your input domain. So essentially, the output of that starts to lose a lot of spatial information because the output of this filter is sensitive to anything that happens everywhere in the image at the same time. So when you switch to fully connected layers, this phenomenon in which pieces of the monkey in a slammed cloud becomes more and more dominant. And you can see here that you see essentially little bits of fur around, maybe some little few stains which look possibly like monkey bits, but it's very hard to recognize a monkey in there. Nevertheless, again, this is for the network, from the viewpoint of the network, this is just a monkey just as good as that one. All right? So this is just a summary slide where you see all of these things together. And here's a video which I thought, so this to me is one of the most interesting things we have found by doing these experiments. So up to here, this is convolutional layers. It's pretty deep already because it's right before the first fully connected layer. You see that the spatial layout of the image is roughly preserved. And you can recognize elements such as the banner there. And okay, maybe that's expected. That means that up to this point, what you see here is what you have here is sort of visual code more than a semantic code. Or maybe it's a mixture of the two. By the way, the reason why this was flickering so much is because each frame of the video is reconstructed independently. And there is, so each time you draw basically a different pre-image by this process of optimization, which is randomized. So every time you reconstruct the next frame, although the difference in the input image is very small, the output, the difference in reconstruction can be pretty big because you might land on completely different points of your image space or fairly different points. But what is surprising again, and maybe I should replay this video, is that here, at the very last level, you see that there is a banner. You see that clearly. Now, the last level here, this is a 1,000-dimensional vector of class labels. All right, so I want this to sink in a bit. Here, what we are inverting is a 1,000-dimensional vector, which with each number should mean what class is in the image. But if we invert that, and that's the only information we provide to the network, we get a banner out. All right, and in the training images, there are no banners. What does it mean? It means that even at this level of depth, the code is still partially visual. It means that it still captures some of the image appearance as such, as opposed to just be completely abstract information, which is, I don't think is completely expected. All right, so this is one way you can visualize deep networks. I'm going to show you briefly other two, which are related. The first one is activation maximization. The formulation is essentially the same. It's also about optimizing an image to based on some criteria which involves a network. But in this case, instead of trying to make the representation the same as a reference one, what we're going to do is to try to maximize one element, one particular neuron in the representation. And you're going to start by doing that by looking at one of these class labels, the ones we just discussed. Okay? So I pick the last 1,000-dimensional numbers, I pick a vector, an element there, and then I try, by a process of optimization, to find an image here that causes this neuron to fire a lot. All right? And again, I do that by gradient descent. So this is just a zoomed in version of that, so you see which neuron I'm talking about. And this is the result I've got. So this is what some people call deep dreams. The original results here were obtained by Karen Simonian, and then we improved on those last year and this year. Can you guess which category this is?
Ducks.
Try again.
Pheasant.
Yeah, close. It's a bird anyway. It's clearly a bird. It's a black swan. All right. I showed you one before. This is instead a
duck.
No, it's a goose. No, it's a duck. All right, it's a duck. Yes. And this is
Hot dog.
cheeseburger. Yes, much better. Much better. I mean, that's pretty clear, right? I mean, the colors are much better than my screen. Maybe that's what's confusing. Yeah.
Teacup.
Teacup. Yeah, that's right. Teacup. Right there. Frog. Yes. It's easy. This one is hard.
It's not visual, because you know.
Kind of. It's I think it's a vending machine. Okay. Anyway, so this is what the network knows about these object classes. You can see that you get sort of nice, dreamy images out, which is nice. But most importantly here, nothing else has been added but the information about which class level you want to reconstruct. All the rest depends on the information which is stored in these filters during the learning process. Okay. And remember that when we do these inversions, we always start from randomized like that, and then we just maximize a neuron to get an image out. So there's no other information that gets into the picture. And of course, I can play the game, not just for the neurons back there, but for any neurons in the architecture. So if I take different filters in Comp1 and do the inversion, I get patches like those. So not very surprisingly, this corresponds to color saturated version of the filters you get in the first layer of, say, any deep network. But if you go down the line, by the way, this sort of halo effect here is due to the fact that we're using this Gaussian smoothing to get the reconstructions a bit more clear. But the important thing is what happens in the middle. And you see that if we move from COM1 to COM2, we get patterns which are definitely more complex. And this continues, COM3, COM4. I believe this is VGG-M as a network. And these are 4 neurons in COM5, for instance. And you can sort of recognize maybe kind of object-like structures, but it's hard to pick or to say exactly which objects these are. This could be, with a bit of fantasy, be a dog face, 2 eyes and a nose. But it's not so easy. So it means that, and here you see one better. I think this is pretty convincing. This is looks a lot more like a dog face. Why dogs, by the way? Because ImageNet has 400 classes of dogs inside. So out of 1,000 classes, 400 are dogs. Okay. Slightly unbalanced, all right? But the point is that it's not so easy, so obvious that you can pick a single neuron and say, all right, this neuron is representing a face, or this neuron is representing a teacup, all right? This happens at the very last level, but for intermediate levels, it's not so obvious. And here you can see a comparison of neurons in different architectures. So AlexNet, VGM, VGG very deep, at comparable levels of depth, where comparable is defined as the same block, convolutional block. And you can see that the complexity of the reconstructions increases as the complexity of the architecture increases, as you might expect. All right, and the last one is characterization. So this was about visualizing typical neurons. Another thing I can do is take an input image, a reference image X0, and then start to change it in such a way that I emphasize certain neural responses. So I can take any layer in my network, look at the strongest activation, say in COM1, and then try to tweak the input image in such a way that those responses, which are already strong, become even stronger. So this is like recognizing a face and then making the name, which has a big nose, and making the nose even bigger, because you want to get a caricature of what the face actually is. So you can get in this way, quote-unquote, visual caricatures or neural caricatures, all right? So this is what happens if I do that. By the way, this is inspired by the work that Google did with that Inceptionist blog that they had a while back. So if you emphasize features in COM2, in COM3, and COM4, you see that you get kind of line segments emphasized. It's more like circular structure, and here are the more, I would say maybe curvy structure. These are more like circular structure being picked out. And you can see that as you go deeper down the network, different things are being selected. When you finally switch to the fully connected layers, it seems that the neurons are much more semantic, because in this case, what you get out is a repetition of the Fox space. It means that this is what the network thinks is relevant for those responses. So by emphasizing those, you have to create copies of the dog face. This is an interesting image because it's a completely abstract pattern, which is not represented in ImageNet. Nevertheless, it does interesting, it behaves, at least for the first couple of layers, exactly like the other ones, which are instead do have a known semantic content. All right? And of course, you can use this for graphics. This was mentioned here already. This is a video of a couple of colleges in Oxford where we have done a characterization by emphasizing, I think, COM3 features. And it looks nice, so you can use this for art as well. Okay? All right. I still have maybe 5 minutes or so. So we'd like to quickly go through the other part of the talk, which is, in fact, a bit more abstract, but I think is at least interesting to know that, well, there are other ways you can use to try to understand networks. So what we have done here was to, instead of trying to do more visualization, to try to characterize statistically what networks actually do. So to do that, we need to discuss representation again from an abstract perspective. So what is representation? Well, again, it's a function that, in a certain sense, takes a semantic similarity and maps that into a vector similarity. What does it mean? It means that here you have 3 images, 2 bicycles and a dog. And these are called congruous because they contain the same object. And these 2 are incongruous because, of course, they contain different objects. So what you want to do with your representation is to take these vectors of pixels and move them into an embedding space, which is the image representation, where these 2 guys are close because they contain the same thing, and these 2 guys are far. Now, if you apply SVM on top, and this property is satisfied, then this guarantees that you're going to get correct classification, all right, if you can succeed. So what you want is to be invariant in the sense that these two are closed regardless of variation in the bicycles which are irrelevant for the class, but at the same time you want to be distinctive, which means that if you now switch to a different class, then you get a big effect on the representation, because you want now this to be different. Now, is this the right way to look at things? Well, this is the classical way computer vision people have been looking at the common representation for a while, but I would argue that it's actually flawed. And the reason is that representations are universal, in a way, or should be, whereas this is task specific. So for instance, if my problem is to tell that these two are cars or not, then of course the embedding should be closed in space. But if my goal is to tell whether X and Y have the same colors, then this should be far away. So what do I do now? Should they be close or should they be far away? Well, this is not something that we can explain with just this notion of invariance. We need something more. So what is this something more? Well, I think the best way of characterizing that is by talking about equivariance. So your input image will change in some ways, and your representation will change in some other ways, which is simple and useful. All right. For instance, here we have an image X of a car, and the representation is just a point into this high-dimensional space. And now what we can do is we can take the car and flip it left to right, and we can ask ourselves, okay, what happened to my feature? Well, your feature is going to be generally different, because so here the transformation is called G, X is the image, phi G of X is going to be a different point in that space. However, perhaps there is a simple map that connects this guy to that guy. So this we call equivariant with this map there, because it's a bit similar to the talk we have seen earlier today, in which you map a transformation in the original domain to a transformation in the target domain. But in this case, the space is different here and there, so this map will not have the same nature. It will just be a map which corresponds to the G you have there. All right. Anyway, it means that if we flip the image, we know how to flip, in a sort of equivalent sense, the features. And of course, this is useful if, when you change the input image but you keep the transformation the same, then the map here is also the same, right? So the point here is that we're going to fix the transformation, change the images, and we want these two equivalents, this map and G, which is the equivalent map, to work in all cases. And this is the equation we want to satisfy, right? We want to be able to move the transformation out of the representation. Now, if your representation was invariant, what happens is that this map, this MG, is actually just a circle in the sense that you flip the car left to right and your representation doesn't change. And maybe this is what you want to do if you want to classify cars and you don't care about whether cars are driving to the left or to the right. Okay? But in general, you might worry about that. So maybe this is not what you want. You want an equivariant representation. But in some cases, the transformation here is reflected by a map in feature space which either does not exist at all, or if it exists, it's essentially impractical. So the representation doesn't do anything useful in relation to this particular class of transformations of the image. So in a way, it does not understand them, all right? Or doesn't know what to do about them. All right, so these are the three cases we can have. So we pick an image transformation G, and then we can have equivariance, invariance, or neither, depending on these three cases I just summarized. So how do we, now the whole idea here is we're going to pick a representation, we don't train it, we just pick one which already exists, and we're going to check whether this property is satisfied or not. So to do that, we take an image, we transform it, in this case we rotate it 45 degrees, and then we compute features like that, and we try to figure out whether there exists, or this one we learn actually, a map MG that can take this representation and give me the equivalent version that I would have got from the rotated image. Right? So again, so what I'm trying to do here is to fix an image transformation and then learn, if it exists, an equivalent transformation that operates directly into the representation space. All right? And this is learned empirically. In practice, going to be a linear map combined with a permutation. Doesn't really matter. It's a simple transformation, all right? And it's learned empirically. So here you see it for hog. Why hog? Because that's easy to visualize. And again, it's not restricted to deep nets. It works for any representation of an image. So here we have hog fishes for dog, the fish, the woman. And here we have the same, but for the rotated dog, fish, and woman. And here we have learner transformation, which essentially applies the same rotation directly in feature space. And if you squint your eyes, you're going to see that these two things are very similar. It's hard to say though, so what we can do is to use inversion to get back a patch which corresponds to those features, and you see that in fact if you apply inversion here and there, you essentially get back the same image. So it means this process actually works properly. All right? And that's the final bit, you can apply this to deep nets. And the point is that in deep nets you have a whole sequence of representation. So you can take AlexNet and cut it after every convolutional layer, or after every fully connected layer as well. And each time, the first bit of the network will give you a representation, and the rest of the network, well, you can interpret that as a classifier that makes a decision about the image content. And you can play this game everywhere, so you can cut the network everywhere. So what can you do then? Well, what we're going to try to do is to take the input image X, transform it, rotate it, so you compute the representation, and then we try to undo the effect of transformation by learning MG, and then we freeze this guy, and we try to classify the image as before. All right, so we try to do that. We learn MG, and everything except MG is frozen. So what does it mean? What are we doing here? So what we're doing is we're rotating the image, computing the feature, ignoring completely the rotation, then trying to undo the effect of rotation at some depth in the network, and using the remaining bit of the network, the original one, to classify the image. Now this works provided that MG effectively can compensate for the effect of the rotation. All right? Otherwise, this would break the classifier. So if you play this game, so this is the original performance of AlexNet on VG on ImageNet, which is about 20% accuracy. Now what you can do is you take G, which in this case flips the image upside down, and so your goat becomes upside down goat, and the classification error now increases from 20% to roughly 60%. That means that ImageNet does not train networks to train invariant to vertical flips, as you might expect. All right? But if you play this game and cut your network at some intermediate point and learn the transformation which reverses the effect of the flip, well, then you can recover most of your performance at least up to COM3. So what's the message here? It means that these COM3 features, essentially, they're not very semantic because, well, you can take a very odd transformation of the input image and compensate almost entirely just by manipulating those features at that level. But if you go deeper in the network, then you see that your task at compensating this effect is harder and harder, probably because the visual features become more and more specialized to recognizing goats as opposed to some other object. All right? So this shows that if you compensate earlier on, then this trick works, and if you compensate further down, it doesn't work as well. Oh, sorry. By the way, that was the wrong graph. That's the graph. Sorry. This one, yeah, I didn't discuss this. This is just if you use the permutation. This one is you actually learn your map, so you need to learn it. All right? Yeah, sorry. Yeah, so as you can see, it works pretty well up to COM5, but it's not perfect because it's very, very, very stable at COM3. All right, I think this is all I can really say, so I'm going to skip the last part, although it was really cool. All right, and I just move to my summary. So, CNNs. First of all, I should remind that these are new. Okay, they've been around for 30 years, but the modern version has been around since 2012. NVIDIA is still, getting us good enough GPUs to actually train these models. So you can expect bigger and meaner CNNs to be trained down the line, which will improve the performance further, I think, in all sort of tasks. So CNNs are far from being saturated, but they might saturate in 5 years' time, who knows? All right, but not yet, I don't think so. At the same time, CNNs are not just bolts of parameters. So the interesting thing about them, which is, as a researcher, is the most interesting aspect of perhaps, is that in these millions of parameters, many interesting visual structures are being learned. All right, I give you a little bit of evidence today, but there are many other elements of evidence you can find around the literature to actually convince yourself that there is lots of interesting things that this network can actually discover automatically in the data. So understanding which one these are and how this happens is actually very interesting. So the problem is, how do we understand that? So one way is to try to come up with a good visualization, but another one, which is probably even more promising, is to try to, break them apart by studying their statistical properties. So take an image, transform it, and see what happens in the network, and try to learn something from it. Okay? And the hope is that as we do that, I'm going to be able to eventually be able to answer some of these questions. For example, what are these networks actually doing? Can we learn some of the tricks that this network maybe are implicitly implementing and use them more in general, beyond deep learning, perhaps? And when we train a network on a data set of 1 million images like ImageNet, how much does the network learn about the visual world? Does it learn just the image labels, or maybe does it learn also about object parts? Does it learn about perspective, 3D information? Who knows? But these are things that we should be able to discover in the future. All right, thank you.
Time for a few questions?
Yep.
There's a striking difference between the clarity of your images and the clarity of Zyler and Fergus's images, in favour of Zyler and Fergus, I think. And that's because they cheat by using the positions of the max.
Yes.
Would you like to comment on whether one can learn more from the cheating version of Zyler and Fergus and your perhaps less
cheaty way? Well, I have to say our latest paper in ECCV is about cheating as well, so we're not cheat-free. But this is a very good comment, and this is a very important difference that, in fact, most reviewers usually don't pick out. So thank you. So the DCOMNet works by recording. So you don't see this very clearly, but whenever here you see max pooling, in DCOMNet you first take an image, do a forward pass, remember the location of all the max pooling switches activations throughout your architecture. Then when you go back, use that information to complement whatever information you get at the top. Whereas what we do is only getting information on the top and then inverting from nothing. All right. So we don't add any other geometric information back, which means that our reconstruction look a lot more messy. That's because the network doesn't have that information, and it's just hallucinating it by finding something that works, but it won't correspond to what you got originally. So if you take DCOMNet's visualization, they look very crisp, but the key reason is exactly because they are preserving these max pooling switches. So where do you learn more? Well, it's not obvious, but the question we're asking is different. So here what we're asking is what information is preserved after this point onwards, and to answer that we need to delete all other information before in the network. So I would say we're answering at least a very different question. So they're asking, well, I'm not exactly sure which question they're asking in the comments, to be honest. It's hard to formulate because it's a bit of an heuristic, and so it's not formalized very, very, very precisely. But what we are asking definitely is different in the sense that we only want to know what information is being preserved after the network has gone through all these layers if we throw away everything that happened before. Now, why is that important? Well, because the layer above, we only see that information. They won't see the pooling switches anymore. All right? So they will have to base their decision on that alone. So what we want to know is to understand what that is. We don't care so much about the previous pooling switches. That for us would be, in fact, just a distraction. All right? So what do we learn? Do we learn more?